this lecture we continue the branch and bound algorithm. In the previous lecture we were looking at the part selection problem, which is about which are the parts that have to be selected to be manufactured in an FMS. So, we looked at this example where there are 4 candidate parts giving us a profit of 12, 10, 8 and 9 and requiring times 20, 16, 15 and 12 and assuming that 45 units of time is available on the FMS. So, we formulated this binary problem and then we rearranged the variables or renamed the variables based on the ratio of the profit to the time consumed, and the problem was rewritten by introducing the y variables instead of the x variables, such that the variables are written in the non increasing order of the coefficients. Now, this would help us in getting the LP optimum, because the leftmost variable will be the variable in the solution if we solved an LP. Then we started the branch and bound algorithm and we reached a point where we had a feasible solution with z equal to 27. So, profit of 27 is possible. It is a maximization problem. So, feasible solution will give us a lower bound on the optimum, which means the optimum is 27 or more, and in each node we solve an LP. So, LP is an upper bound for a maximization problem. So, we stopped here where we said that we have to proceed from this node, because this has an upper bound of 28.125 and the best value so far is 27. We can get a 28 if it exists. So, we should try and get that 28. 28 comes because all these objective function values are integers and therefore, the optimum solution will be an integer. So, 28.125 is effectively 28. So, now we proceed here with y2 taking a value 0 or 1. So, this is y2 equal to 1 and this is y2 equal to 0. So, this gives us 2 nodes. This is y1 equal to 0, y2 equal to 1, both of these are fixed. So, y1 equal to 0, y2 equal to 1 means we use 16 units here. So, 29 units are available. So, y3 will be 29 by 20. So, y3 will be 29 by 20 and the objective function value will be 12 into 29 by 20. 3 into 29 is 87 by 20, 87 by 5, 17 5s are 85, 17.4 plus this has y2 equal to 1. So, 17.4 plus 10, so this gives us a bound of 27.4. So, now we use the condition, since it is a binary problem and all these objective function coefficients are integers. So, at the optimum the objective function value has to be an integer. So, if we proceed from here, we can only get the lower integer value of this or less. We could get 27 or less. We already have a solution here with 27. So, we do not need to proceed from this. So, this is fathomed because upper bound is equal to lower bound. Upper bound is 27, lower integer value of 27.4. So, upper bound is equal to the best lower bound. So, even if we proceed from here, we can get only 27 or less. So, we do not proceed. Now, the other one is y1 equal to 0, y2 equal to 0, which means both are kept at 0, 45 units are available. So, y3 equal to 45 by 20. So, y3 equal to 45 by 20 and objective function value is 12 into 45 by 20. So, this is 3 by 5 9, so z equal to 27. So, once again from here upper bound is 27, proceeding we can only get solutions with 27 or less. So, we do not proceed. So, we fathom here by saying upper bound is equal to lower bound. So, we do not have any more nodes to proceed. So, this is the optimum solution. So, this gives us a solution with this is y1 equal to 1, y2 equal to 1, y4 equal to 1. So, y1 equal to 1, y2 equal to 1, y4 equal to 1 with profit equal to 27 and 12 plus 16 28 plus 15 43 units of time are taken and 2 units of time is not used. This is the same solution that we got when we solved it by integer programming. Now, one of the reasons you look at a branch and bound is, one is the time taken as such by a branch and bound could be little less than the time taken to solve this using a solver, and in the event we do not have a solver, then we could use this branch and bound algorithm and solve it. Branch and bound algorithm uses principles of lower bound, upper bound, relationship between linear programming and binary IP and so on. So, branch and bound also gives us the optimum solution, and branch and bound to solve knapsack problems are extremely popular, and one can easily write a branch and bound code to solve this. Well, now if we do not want to try and get optimal solutions, and if we are looking only at heuristic solutions, then let us see what happens. Now, let us look at this one and try to get some heuristic solutions. So, this is the formulation. So, we simply take these variables as they appear and see whether we can make them. So, y1 is the variable or the product that actually has the highest profit, their profit per unit time, even though in terms of highest profit 12 is the highest, but it requires 20 units of time. So, profit per unit time, the highest ratio happens to be for the variable y1. So, we start from the left and say y1 equal to 1, z equal to 9. Now, when we put y1 equal to 1, 12 units are taken away. So, 33 units are available. y2 requires 16 units. So, y2 is equal to 1, z is equal to 9 plus 10, 19. So, y1 equal to 1, y2 equal to 1 would take 28 units. So, 17 units are available. Now, we look at y3 equal to 1, y3 requires 20. So, y3 we do not produce, y3 equal to 0, and then we go back and check for the 17 what happens to y4, y4 requires only 15. So, this gives us y4 equal to 1 with z equal to 9 plus 10 plus 8, which is 27, which is the same optimum solution for this particular instance. But if we had not sorted the variables, and if we had tried to solve this problem as it is without sorting or rearranging the variables, and if we apply this heuristic, now we would start with x1 equal to 1, z equal to 12. Now, x1 equal to 1 takes away 20 units of time. So, 25 is available. So, this would give us x2 equal to 1 with z equal to 12 plus 10. So, we have used up 36 units and we have 9 units. So, x3 we cannot do, x4 also we cannot do, and therefore, we end up getting a solution with 22 as against 27. So, if we apply this heuristic, it is very necessary that we sort the variables according to the coefficient, and then we choose the variables in the order of non decreasing value of this coefficient. Now, we should also bear in mind that this, after sorting, it need not give us the optimum solution all the time. It gave us, this heuristic gave us the optimum solution for this particular example. But if there is another example where the optimum solution happens to be say 1, 3 and 5, if in 5 variables, this heuristic sometimes can give us 1, 2 and 4, which is lesser in terms of objective function value than 1, 3 and 5. So, we could have situations, where 1, 3 and 4 would be optimal, whereas the heuristic could show 1, 3 and 5, 1, 3 and 5 could be optimal, whereas the heuristic could show, or 1, 3 and 4 could be optimal, whereas the heuristic could show 1, 2 and 5. So, we could get into situations like this. So, this heuristic need not give us the optimum solution all the time, but nevertheless it is a very effective heuristic, particularly when we take into account the ratios and the order of the variables based on that. So, this is how the part selection problem is solved in flexible manufacturing systems. We now move to the second problem, which is called the machine loading problem, which talks about balancing the workloads subject to allocating each job to only one machine. There is a tool slot requirement and capacity. So, we will explain this problem through an example. Now, this example is for the machine loading problem. Now, here we assume that we have done the machine grouping problem, which was one of the production planning problems listed. So, the machines are grouped together and there are 2 machines. Now, there are 2 machines and we have to load 7 jobs on 2 machines. Seven jobs on 2 machines. Now, the processing times are given there. There is also an additional tool restriction which we will consider. Now, if we do not have this tool restriction, then the problem is simply one of allocating 7 jobs on 2 machines to minimize make span, This comes under the category of non-identical parallel processors, n jobs, single machine, but non-identical parallel processor, which means 7 jobs on a single type of machine, but 2 machines are available. Processing times are different on different machines. Identical parallel processor means the processing times are the same on both the machines. Here you can see that job number 1 takes 1 unit of time if it is done on M1 and 2 units of time if it is done on M2. But now we also have tool requirements which are there. Now we have to say that each machine M1 has a tool drum with capacity of 10 tool slots. Typically the side view of a tool drum would look like this. There will be a tool drum like this with slots here. So, we would assume that there are 10 slots, 10 slots where tools are inserted. Now, each job would require certain number of tools. For example, I can allocate 1, 2 and 3 to the first machine because the tools required is 8, 2 plus 3 plus 3. I cannot do 1, 2, 3 and 4 to the first machine because the tools required is 12. It can accommodate only a maximum of 10 tools it can accommodate. Now, the load balancing problem is also a problem which minimizes the make span in some sense. When we try to balance the load on both the machines, At the end what we are trying to do is, as long as the balance results in a smaller amount of time on both the machines, as small a time on both the machines. Now all the 7 jobs are going to be done in parallel. Now suppose we allocate as in this example, suppose we allocate 1, 2, 3 and 5 to the first machine, and we allocate 4, 6 and 7 to the second machine. Suppose we do that, then on each machine the 10 tool slots are going to be occupied. So it is feasible. So what we are going to assume is, these jobs 1, 2, 3 and 5 are available, they go to the first machine, 4, 6 and 7 go to the second machine one after another. But when these 4 jobs are allocated to the first machine, the 10 tools that are required are fixed on the tool drum. So when the work begins, these 4 jobs are taken one at a time, the tools are all available, and in one batch they go to the first machine. Similarly, 4, 6 and 7 go as one batch to the second machine, and all of them can come out once the entire processing is over. Sometimes we may even have a situation that the job goes, there are enough tools, the work is carried out, the job moves, the next job comes and so on. So each job is completed at certain point in time, but all the 4 jobs are completed on M1 at a certain time, and all the 3 jobs are completed on M2 at a certain time, and that time is what we are going to balance, so that all 7 can be completed within a certain amount of time, which is minimized. So the problem will be like this. So the problem will be like this. There are 7 jobs and 2 machines. So Xij equal to 1 if job I is assigned to machine J, job I is assigned to machine J. Now each job goes to only one machine. So sigma Xij equal to 1 summed over j for every I. Each job goes to only one machine. The tool constraint has to be satisfied. So sigma summed over I Ti Xij is less than or equal to 10 for every j. For each machine, the number of tools required based on the jobs is less than or equal to 10. Now the load on the first machine will be sigma Pi Xij or Pi Xi1, and the load on the second machine will be sigma Pi Xi2. Now we want to balance the load, so we want to minimize the maximum of these two loads. So we will minimize U such that U is greater than or equal to this, U is greater than or equal to this. We want to minimize the maximum of these, so U is greater than or equal to all of these. So this will have 7 constraints that make sure that each job is assigned to one machine. This has 2 constraints to ensure that the tool requirement on each machine is met. This is one constraint, this is one constraint, and the objective function is to minimize U. So we can solve this. This is also a binary problem where Xij equal to 0, 1, but there is an additional U greater than or equal to 0. So it has 14 binary variables, and one u which is either a continuous variable or a integer variable, because processing times are all integers. So, when we actually solve this, we get jobs 1, 4, 5, 6 are assigned to machine 1. So, jobs 1, 4, 5, 6 are assigned to machine 1, jobs 2, 3, 8 are assigned to machine 2, 2, 3, 7 are assigned to machine 2. Now, when we do this, job 1, 4, 5, 6 on machine 1 has time 1 plus 8, 9, 9 plus 6, 15 plus 7, 22. The tool required are 1, 4, 5, 6, 4 plus 2, 6 plus 4, 10, 2, 3, 7 on machine 2 is 6 plus 5, 11, 11 plus 7, 18. In terms of tool requirement, 2, 3 and 7 is 3 plus 3, 6 plus 4, 10. So, the loads are 22 and 18, the most balanced load is 18. If we had looked at 1, 2, 3 and 5 on M1, if we look at 1, 2, 3 and 5 on M1, 4, 6, 7 on M2, if we look at an alternate solution. So, 1, 2, 3 and 5 have tool equal to 10, 4, 6, 7 also have tool equal to 10. So, they satisfy all these constraints, these two. Now, we come here, the load on M1 is 1, 2, 3 and 5, 1 plus 4, 5 plus 7, 12 plus 6, 18, 4, 6 and 7 on M2 is 7 plus 8, 15 plus 7, 22, 22. So, again this has a solution with 22. So, it is an alternate optimum. The solver has given one of the solutions with maximum value equal to 22. But on the other hand, if we consider another feasible solution, which is 1, 2, 3 and 6, if we consider 1, 2, 3 and 6, we do 4, 5 and 7. So, 1, 2, 3 and 6 again tools is satisfied. So, 1, 2, 3 and 6 is 4 plus 1, 5 plus 7, 12 plus 7, 19 on M1, 4, 5, 7 on M2 would be again 8 plus 7, 15 plus 7, 22. So, we again have another optimum solution. So, we have multiple alternate optima. In this case, the solver has given one of them. 4, 5, 7 on M2 is 7 plus 7, 14 plus 8, 22. So, we have this. So, it is given one of the alternate optimum, which is this. Now, the advantage of doing this, balancing the workload to try and minimize the maximum, is to ensure that in 22 time units in this particular solution, all the 7 jobs are now completed and they can go to the next stage. It is like minimizing a make span, but all 22 jobs are completed. Now, we could also look at in terms of if there are due dates, then the problem becomes a little complicated because the sequence comes into the picture. Here we do not bring due dates into the account. So, it is essentially an allocation problem. This problem does not actually talk about at what time one out of each of these 7 jobs are coming out. It does not say that. It is only an allocation which says machine 1 is utilized for 22 time units, machine 2 is utilized for 18 time units, and therefore, all of them, since they are done in parallel, all of them are over in 22 time units. But if we had individual due dates for each of these, then we get into loading and scheduling problem, which becomes little more complicated. Now, which job will go to the other one is and at what time, what order will it go now the variable changes, so it becomes a scheduling sequencing problem. Therefore, the variables now have to look at time, particularly time, because we are talking of scheduling and due dates. So, when we bring due dates explicitly, the decision variable also changes. Now, we could think in terms of a simple heuristic to solve this problem. So, a simple heuristic would be like this: each job is now allocated to the machine where it has the least amount of processing time. Now, we could look at two machines M1 and M2. A simple heuristic would be take each job and allocate it to the machine which has least processing time. So, job 1 will go to M1, job 2 will also go to M1, job 3 will go to M2, job 4 will go to M2, job 5 will go to M1, job 6 will go to M2, job 6 will go to M1, and job 7 will go to M2. So, 9 and 7, so job 7 will go to M2. Now, we have to check whether this satisfies the tool requirement, because if it does not satisfy the tool constraint, then we will not be able to run this whole thing in a single batch. So, we look at 1, 2, 5 and 6, 2 plus 3 5 plus 2 7 plus 2 9. So, this is satisfied. 3, 4 and 7 is 3 plus 4, 7 plus 4 11. So, this is violated. So, we cannot implement this, because for 3, 4 and 7 put together the tool constraint is violated. So, but let us just simply add the processing times to see where we are. So, 1, 2, 5 and 6 is 1 plus 4 5 plus 6 11 plus 7 18, and 3, 4 and 7 5 plus 7 12 plus 7 19. If this were implemented or implementable, then the load balance happens and at time equal to 19 all the 7 jobs are out. But unfortunately, we are unable to implement this because the tool constraint is violated. So, we could think in terms of either an exchange, or we could think in terms of some other kinds of problems. For example, we could now think in terms of taking something out of this. So, we have to remove one of these 3 or 4 or 7, such that we are within the 10 tool slots. If we look at 3, shifting it from M2 to M1 is going to increase the time by 2 units. If you take M4, it is going to increase by 1 unit, and if you take M7, it is going to increase by 2 units. Therefore, if at all we really want to take something out, we can choose either the one which has minimum increase on the other one, or in terms of tools. So, let us try to put M4 there. So, we now take this and go put M4 here. If we do that, now 3 and 7 gives us time equal to 7, but 1, 2, 4, 5, 6 is 1, 2, 2 plus 3, 5 plus 4, 9 plus 2, 11 plus 2, 13, correct, 13. So, from 1, 2, 4, 5, 6, we have to shift things here such that the time is minimum, and whatever we shift, we are able to transfer at least 3, a job that has 3 or more tool requirement has to go. So, we look at jobs that have 3 tool requirement. Job 2 has tool requirement of 3. In fact, job 2 is the only one that has tool requirement of 3. So, if we shift it, then we shift by 2 units. So, 2, 3, 7 will come here, 1, 4, 5, 6 will go here. If we do that, the original values were 18 and 19, that were the original values. So, when we shifted, it became, we first shifted 4, so it became 18 plus 8 26, 19 minus 7 12, so it became 26 and 12. Now we shifted 2, so 2 became, here it became 18 and here it became 22. So we get one of the alternate solutions with 1 4 5 6 and 2 3 7. We did this for a very small problem, we did this by looking at the problem, but we actually realized that if the problem is large and this itself has a large number of jobs, then it is not only necessary, the problem is a little tight in the sense that the sum of the tools adds up to 20, the requirement adds up to 20 and the availability is also 20. Suppose the availability was 22 and the requirements were 20, then this solution itself, first solution itself would have been optimal. Or the point I am making is, when we actually move, all that we need to do is we need not choose only one job at a time to move, we could even choose 2 jobs at a time to move, such that the total tools saved, we are able to bring it back within feasibility. So that also becomes a binary knapsack problem, which we actually solved in the part selection problem. So that is also similar to a binary knapsack problem. For example, if we choose to move, if when we started with this, we started with 3 4 7 and 1 2 5 6. Now when we did 3 4 7, we realized that the excess tool was 1. So which ones to go here will be like this, it will be like minimize, if y3 equal to 1 if 3 leaves, y4 equal to 1 if 4 leaves, y7 equal to 1 if 7 leaves. So if 3 leaves, the minimum increase is 2. So 2y3 plus 1y4 plus, for 7 also it is 2y7, such that job 3 requires 3 tools, 3y3, job 4 requires 4 tools, 4y4, job 7 requires 4 tools, 4y7 is greater than or equal to 1, because the excess was only 1. 3, 4 and 7 together have 11 tools, but then 10 is the availability, so the excess is 1. So whatever goes out should take away at least 1 tool. So this itself is a binary knapsack problem, yj equal to 0 1. So we could solve a binary knapsack problem into it and then choose which one will go. So here what I have done is I have given a solution where we interchange. We could do interchange as a way to get it, or we could solve binary knapsacks, or we could simply allocate from one machine to another till we get feasibility. So this is how the load balancing problem is solved in the context of FMS, but we need to look at few more aspects of the load balancing problem. Now we are introducing something that is very unique to FMS, which is called tool slot saving. Now let us go back to the same problem, and if we had allocated the jobs based on minimum processing time, we would have got 1 2 5 6 for M1 and 3 4 7 for M2. We also found out that this had 18 total time, this had 19 total time, and the tool requirement was 9 and 11. Now we said we are not able to implement this because if I put jobs 3, 4 and 7, together, I need 11 tool slots from this. If you look at 3, 4 and 7, I need 11 tool slots from this. Now, let us go back and understand how it works here. Now, job 3 requires 3 tools, job 4 requires 4 tools, and job 7 requires 4 tools. Now, can we have a situation where right now when we say a total of 11 tool slots are required to put these 11 tools, we are going to assume that none of these tools are common. Now, suppose we have a situation where these 3 tools and these 4 tools have one tool in common. Suppose they have one tool in common, then we actually do not need 11 tool slots, we need only 10 tool slots. So, understanding the common tools and bringing them in can not only save the tools and tool slots, but it can give us a solution with 19 instead of a solution with 22. If we are able to find that amongst these 3, 4 and 7, one pair at least has one common tool, then I do not need 11 tool slots, it is enough for me to do with 10 tool slots. So, that is what we want to show here when we do this with tool slot savings. Now, when we do this with tool slot saving, now we are going to assume that if we put 3 and 7 together, we can save 2 tool slots, which means 3 and 7 together, they do not need 4 plus 3 7, but they need 5. 4 plus 3 7 minus 2. 1 and 3 put together, I can save 1 tool slot. 6 and 7 put together, I can save 2 tool slots, and 4 and 5 put together, I can save 1 tool slot. Now, when I start doing this, now I know that the solution with 18 and 19 is feasible, because based on minimum processing time, I have allocated 1, 2, 5, 6 to M1, 3, 4, 7 to M2, 3, 4, 7 together has 11 tool slots, but by putting 3 and 7 together, I can save 2, so I need only 9 tool slots. So, this solution is feasible. But what are the other issues that come when we do this? Now, let us continue and then let us look at the a few other things to do this. Now, let us, instead of having 10 tool slots, let us look at 8 tool slots. Let us assume that this drum can accommodate only 8 tool slots instead of 10 tool slots. So, we now begin with, this is the minimum processing time solution. This is the minimum processing time solution. Now, this requires 10 tool slots, this requires 11 tool slots to begin with. Let us also write these 3 and 7. I can save 2, 1 and 3 I can save 1, 6 and 7 I can save 2, 4 and 5 I can save 1. Initial allocation is 1, 2, 5, 6 and 3, 4, 7 that we have. Now, we consider M1, both are infeasible. So, we move job 1 to M2. So, when we move job 1 to M2, we get into another solution with M1, M2, 2, 5, 6, 1, 3, 4, 7. 2, 5, 6 2, 5 and 6 is 7 slots. 1, 3, 4 and 7 is 2 plus 3, 5 plus 4, 9 plus 4, 13 are here, but 3 and 7 gives us 2, 1 and 3 gives us 1, so this becomes 10. Becomes 10. So we get 7 and 10. Now M2 is infeasible, so we move job 5 to M1, 1, 3, 4 and 10 to get the allocation, 2, 4, 5, 6 and 1, 3, 7. So we move job 4 to this. So M1 has 2, 4, 5, 6, 1, 3, 7 on M2. So we go back and check 2, 4, 5, 6, 2, 4, 5, 6 is 4 plus 3, 7 plus 2, 9 plus 2, 11, 2, 4, 5, 6, so this is 10, 1, 3, 7 is 3 again, 2 plus 3, 5 plus 4, 9, 9 minus 3, 6. Now you realize 2, 4, 5, 6, so 5 can be moved here to get 8 and 8. So finally we get the solution 8 and 8. So 2, 4, 5, 1, 3, 6, 7, 6 can also be moved. So we can get 2, 4, 5, 1, 3, 6, 7 with 8 and 8 to get a solution with workloads 18 and 23 respectively. So we could do this. Right. Now we look at the rest of them, but after we look at a few more things. So let us come back here. So given a certain tool drum capacity, we can now have an algorithm which will finally take us to that solution. But we will realize that this algorithm is not so very well defined, in the sense that we simply looked at the problem and said we will shift 5 or we will shift 6 and so on. But each shifting we have to solve a single constraint problem. Let us also look at a couple of related issues. When we say that tool slot saving can now be incorporated, now can we go back and solve this optimally? Now to solve this optimally, this constraint will be Ti Xij minus saving is less than or equal to 10, because the very advantage is the saving that we could consider. But then we realize that this saving cannot be very nicely represented here, it will become non-linear. I can save 2 if x32 equal to 1 and x37 equal to 1. So the saving will be 2 into x32 into x37. Only when both of them are 1, I get the saving. If one of them is 0, I do not get the saving. So it becomes non-linear. So the problem becomes non-linear. That is the first part. Similarly, if I am looking at moving one from this to the other or from the other one to this, and if I end up looking at the problem once again as a knapsack problem, once again I get a non-linearity coming in, because when I move one, the next one it again has a non-linear term, because I gain by when I move one job from M2 to M1. Now I save something on M2, at the same time I have to go to M1 and also look if there is a saving because a new job comes in. And not only that, when I actually release something from M2, for example, if I am releasing job 6 from M2, by releasing job 6, if job 6 alone requires, if job, for example, if I have a situation where let us say I am releasing job 7 from M2, I am releasing job 7 from M2 to M1. By releasing job 7 from M2, I am not exactly saving 4 slots, because if 3 and 7 were in M2, together I have already saved 2 slots by putting 3 and 7 together. Now by releasing 7, 3 would want those common tools. So I am not saving 4, but I am saving only 2 slots, because 2 out of the common tools are still required. So that also has to be brought in when we actually move jobs from one to another. So non-linearity will create a lot of issues when we do this, particularly either when we try and solve this here or we try and solve this here. It is not impossible to do that, but non-linearity will bring in issues. Now the knapsack problem has to be modified. So there is a branch and bound algorithm which has been published by Barada and Steck, which takes into account this non-linearity, and then it develops a branch and bound algorithm to do load balancing, considering tool slot saving also. But one has to understand that the non-linearity will come in here as well as here, because when we release, we do not actually save 4 slots, we save less than that if 3 and 7 had belonged to job 2. Similarly, when 7 goes somewhere, we then need to adjust the slot requirement there, which is an important aspect. Now continuing on this further, now there is also in practice there is also a due date dimension. These jobs will have to go to the customers at certain specified due dates. So the moment we bring in due dates, we get into a typical scheduling problem where time of completion becomes a variable and the problem becomes complicated. Secondly, we also, if we look at this particular problem that we have example that we have solved, we have 7 jobs, and the way this problem is created, a total of 20 tool slots are. Let us even forget that we are going to look at tool saving constraint. Let us look at the problem as it is without a tool saving constraint. Now total tool slots required is 20, total tool slots available is 20. If there were tool saving, we were able to solve when we had 8 tool slots available, which means with 16 availability and 20 requirement and 4 saving, we were able to get this. But suppose we have about 20 jobs and we have 2 machines. Let us say the tool capacity is 10, but these 20 jobs put together require about 40 tools. Number one is we may not actually have, we may have only 20 tools corresponding to the tool drum. The point is now these jobs have to be allocated to these machines, and then let us assume for the sake of discussion that the first 10 jobs go to M1 and the next 10 jobs go to M2. The requirement of tools for the first 10 jobs would exceed 10. So the first 10 jobs will have to be run on multiple batches, because the 10 tool slots will now be set up, a subset of these 10 will be done with this, and then the second part of that 10 will have to be done again when these tool slots are either retained or some changes are made to this depending on the requirement of the other jobs. So there is also a batching problem. So when multiple jobs are there on machines, which job is allocated to which machine, which job will go to which batch, because the reason is between every batch some tools will be removed and some tools will be brought in. So there is a tool changeover time between every batch. So which batch will it go and when will it be scheduled, and if there are due dates, there is a due date problem, there is a batching problem, and there is a load balancing problem. So there are 3 different problems that come in, and in addition to that there is a non-linearity that comes in when it is possible to have changes tool slot, when it is possible to gain tool slots if jobs have common tool requirements. Now this common tool requirement is also something interesting. Now we could say that 3 and 7 gives us saving of 2, 1 and 3 could give us a saving of 1. In our calculation, if we put 1, 3 and 7 to the same machine, we will go back and say 1, 3 and 7 requires 9 tool slots. There is a saving of 2 here, there is a saving of 1 here. So, 9 minus 3 is equal to 6. It could be 6, it could sometimes be 7, because it might happen that 3 and 7 I can save 2 slots. 1 and 3, if it requires the same tool slot, then can I subtract? Or if 1, 3, now it depends on which are the tool numbers. Which are the tool numbers is another question that we could have to look at. Sometimes we may actually have to define them exactly in terms of tool numbers and then see what is the saving. So, when we actually do this, when 2 of them have savings, there could be an intersection that comes which has to be added. So, the one may not be an effective tool saving. So, that can also happen. So, the nonlinearity is actually further compounded by multiple. For example, when I do 1, 3 and 7, I might say I will save so much. If I do 1 and 3, I have this much saving. I have 3 and 7, I have this much saving. When I do 1, 3 and 7 on the same machine, it may not be the sum of these two, but it could be something else. So, the nonlinearity is further compounded. So, the machine loading problem becomes an interesting problem and more involved when we have multiple batches, when we have tool slot saving, when we have due date related measures. So, this problem is necessary and useful, so that the time taken to produce on an FMS is reduced by properly solving the machine loading problem. Other problems related to flexible manufacturing we will see in the next couple of lectures.